Well, good afternoon, and welcome to Comp 422 and Comp 620, Information Privacy and Security. Today we're talking about, uh, maybe we will talk about reverse engineering, and we'll do a review for the final exam. Then I'll make a few final comments. Okay, reverse engineering is where you try to figure out how it works when you try to take apart a device and see how it does. So definitions, determining how it accomplishes that with little previous knowledge. Mostly it can be machines, it can be software, where you kind of look at how does this thing work? Often from software, you have the executable version, and you want to know how does it work? What are the code inside? And it's been out there for a long time. Example here is that the early IBM PCs were not, well, a lot of them were not made by IBM. Almost right after the IBM PC came out, people started making clones or computers that worked just like the IBM PC, and they of course reversed engineered the BIOS. There are tools to help you do reverse engineering. As you should know, a compiler is a program that takes the source code and converts it to machine language. A decompiler goes the other way. A decompiler takes the machine language and converts it back to source code. There are several programs out there to do that, free ones and not so free ones, that will decompile different languages, Java bytecodes or executable language. When you compile a program, there is an option to save debugging information. It'll save the variable names and where they're located. This makes it nicer when you're debugging because debugger will know what line of code each part of the machine language is. It knows the names of variables. That's an option when you compile. You can turn it off, turn it on, nothing. If you leave it on, then when they reverse engineer, you can easily tell not only what machine language location you're using, but the name of the variables in the high-level language. Okay, why do you want to do this? Well, sometimes you have to make a system that interacts with another system, interoperability. And you need to know what is it really doing inside. You need your software to interact with this, and what is that software doing? And sometimes you're dealing with programs that you don't have the source code anymore. Sometimes in an industrial setting, you've got an old system and nobody knows whatever happened to the source code for that system. It's not around anymore. And so you've got to make the system do it. Or you have an old code and you don't know how it works and you need to upgrade it. So you got to reverse engineer it, figure out how it works, and then change it. Also, of course, espionage. Sometimes people want to look at how does this program work? Corporate, stealing from other companies. You might look at their program and say, gee, how do they do that? And you might reverse engineer their program and try to use it as yours. The national labs are interested in students knowing about reverse engineering. It was their suggestion that we have this lecture today. The Lawrence Livermore National Lab in California, where a large number of A&T students have gone to work or be interns. They are very interested in malware reverse engineering. They want to know if malware that comes into their systems is just general malware that attacks everybody. You see it all over the place. Or is this malware that was made to attack the national labs? Because they do secret things at the national labs, and they don't want those secrets to get out. And they're very concerned if somebody is maliciously trying to attack the national labs, as you might expect. So they're making sure that the software is just general malware, or is somebody trying to break into the national labs. Oh, and of course, is this all illegal? The big answer to that is, well, maybe. As you can see, the Digital Millennium Copyright Act, which was about 20 years ago or more, states that it is legal to reverse engineer to circumvent protections to achieve interoperability between computer programs. On the other hand, I believe they kind of said you can't break the copyright protection systems that systems have. Whereas some software has anti-copying provisions, and you're not allowed to break those. If you read the end user license agreements that come with almost all software, when you buy something, it has a little button. Click here that you agree with the license, which most people never read. If you go out and read those, sometimes they're very interesting. They almost always say you cannot reverse engineer this software. Having said that, some courts have said, well, that may not be legal, but as a general rule, they don't want you to take apart their software. And of course, as a software creator, you'll understand that the companies have spent a lot of time and money creating the software. They don't want somebody else to steal it for nothing. When you're looking at how a program works, you can find out a lot about it just from dump of the memory. Because if you don't have the source code, you want to know what's doing. Well, you can look at the memory of the program. I'm going to cover a little bit of that. It's getting right down and looking at the bits and bytes. Not only do you have the memory of the program, but you have the stack trace. Those of us with long gray beards remember back in the days when this was your debugging technique. You didn't have all the systems you have now to help debug your system. And so when your program didn't work, when it terminated incorrectly, you could look at the memory dump, look at the systems would copy the contents of memory out to a file along with contents of the registers. And they didn't have programs to assist you in looking at the memory dump, trying to figure out what's going on. I even wrote a program that analyzed memory dumps for a specific system. Let's look at my sample program here. It is very simple. This is in Java, but the content, Java. No, this was in C++. Sorry, C++. Looks almost like Java. It's in C++. We have a main program. The main program calls method A. Method A does some stuff, and then calls method B. Method B does some stuff, and then returns. Okay, that's it. Each time you call a method, the software automatically creates a frame, an activation frame on the stack where it keeps information about that call, keeps the parameters, what parameters are you passing to the method, return address, how do you get back? The frame pointer, which points to the previous frame, which is useful. If something goes wrong, it can then print the stack trace. Often, it can particularly noticeable in Java. If something blows up, it gives you this long list of this method calls this method, calls this method. It does that by going back through the frame pointers. And then local variables are also stored on the stack. So let's start here. We know from the software where the methods start. The main program started these, and this is easy to find out. Where are each of the methods located in memory? And the EBT pointer, the extended, this is a frame pointer. It is I don't remember what, B is in pointer, E is extended, and B is, B, points to the frame pointer at the current time. What is the current frame pointer? And when a program accesses its local variables in the method, they are referenced off the EBT register, the frame pointer. Okay, so the frame pointer, let's say, is pointing to 12360, which is this address in memory. So this is the memory in hexadecimal. Here it is. We have the frame pointer. So BBT is pointing to the frame pointer, and this frame pointer, the beginning of that, points to the next previous frame pointer, and so forth. There's return address is the next 4 bytes. This is an Intel machine. Intels are what they call little endian machines. There's little endian machines and big endian machines. Little endian machines store the bytes in reverse order for integers or addresses. It's long and complicated why they would want to do that, but they do. Big ending machines do it the other way around. So the bytes will be reversed. The bytes are reversed, but not the bits in the bytes. So if you look at this first address here, which is 60148000, no, that really the address is 00801460. So 00801460. That's going to be in method A. That return address is in method A because it's 081460. Well, it's beyond this one, not up to this one on fast enough. So this is only 3 methods in the program. It's going to be in method A, someplace 60 bytes into method A. Yes, question.
Wait, what happened to the 6?
The 6.
Yeah, it's not on.
Well, here, this is the start address of those methods. So this the program, there's a program, you're in method A, somewhere here, not the beginning of method A, we call method B. So it's not the start address of method, but it's somewhere into its 60 hexadecimal bytes into method A called method B. Okay, so you got to look at in which range, where was it? Between these two, between those two. So now we know it's between this and that. So it's got to be in method A. So this is an address in method A. And there's a local variable 9. Wrong word, excuse me, backing up. Yes, there's a 9. We started with a, yeah, okay, goat and cows and 3 and 5s and 8s and, yeah, okay. I'll multiply them together. Anyway, the answer is 9. So we're past 9 as a parameter because here is, anyway, close one. So big point of this is not that I'm going to ask you to look at a memory dump, which I have done in other classes, but I'm telling you that you can find out a lot about what the program is doing, what's in memory. Also, all these C's, those C's are stack canaries. All those C's are put there by the compiler to tell you that this code, this location memory should not have any values. And when it goes to return, it checks these values. Are they still C's? If they're not C's, it goes, oh, something is overwritten the end of that variable, and there may have been stack overflow. So the return address may no longer be valid, so it stops the program right there because it doesn't want to return because it may not return to the right location. That was a C program. You can do the same thing for Java. Java programs, source code is compiled in byte codes. Byte codes are kind of like the machine language for some imaginary machine. The byte codes are then interpreted by the Java virtual machine. They're usually not just interpreted, they are compiled from Java bytecodes into machine language, which is then executed by the Java virtual machine. But you can reverse engineer these. You can take a jar file, which is a collection of object codes, such as class files, and convert that back into machine language. Again, if you use the option that saves the debugging information, it will save the variable names and everything. Some of the programs are very good. I tried a couple of them. Here's a simple Java program. It's kind of like, it's almost exactly the same as the previous example. So I compiled this one, took the Java bytecodes, ran them through a decompiler, and this is what I got. This is almost the same. There's a few changes here. If you look, okay. Yes, I have in cow goat. And then I said, well, it put the initialization in there when it compiled it. It doesn't even have cow, it just puts goat there. It figured out carefully that we don't need, see, it returns cow. This takes cow and returns it. Says, you don't need that. Probably because the compiler, when the compiler actually compiled the program, it realized that cow was redundant, unnecessary, and never really used it. So this is probably what was actually created. But you can see it's almost identical. Pulled up the same variable names because they were available in the class file. Now, it's important to note that if you can take the machine language or the byte codes of a program and convert them back to source code, that if you have any secrets in the source code, such as encryption keys and the like passwords, if those are in the source code, they can be uncompiled and read from the uncompiled program. So you have to be careful about that if you're going to run it. Particularly sometimes you have to release the byte codes. We always have to release the executable if someone's going to execute it, and they can take the executable apart. Sometimes in virtual languages like Java or Python, where the compiled version is just like, well, Python, of course, doesn't create a compiled version. It just gives you the source code. You have to look at it. There are things you can do about that. There's obfuscation. Obfuscation is rearranging the source code of the language so it's difficult for humans to understand. It still executes in the same way, or produces the same results as the original, but it's hard for humans to understand. They use different things. I'll go over what they do. And so even though it executes, it's more difficult to figure out exactly what it was doing. Companies do this because sometimes they don't want their source code out, and so they're going to obfuscate it. So if somebody reverse engineers, it doesn't look nearly as good. And of course, you do those simple things like you don't use the debug option, so it doesn't save the variable names and the locations, so people don't have that kind of information. And while obfuscated code is more difficult for humans to read, it still executes, and it's not impossible to put it back. It's a sense of security through obscurity. They're making it difficult, but not impossible to read. You can still put it back. In fact, you could write a program to unobfuscate some code, and there are such systems out there. There are tools you can get on the web to do obfuscation, and then there are similar tools to undo the obfuscation that you find. So if you look at an obfuscated file, it will, and kind of put the things back. Sometimes obfuscated code is smaller because they optimize it along the way. And here's a question for today. The cards. B, everybody likes B. B is also the most common online. Anybody else online wants to vote? Anybody want to wake up? Okay, almost everybody voted B. Too bad B is not the right answer. It's C. Okay, if you're going to protect the information, you need to use the server's public key. Private key, if you have it in the source code, that's the public key is what everybody knows. The public, by name, by virtue of its name, everybody can find out the public key. That's what's in the certificates, is the public key. So you want to use the public key, send it to the server, and then the server knows the private key, and they can decrypt it. So everybody's going to encrypt it with the public key that's well known. So in other words, the trick here is you're going to put this in the source code. But who cares? Because everybody can see it. You're not releasing a secret. People can find out the public key easily. And the server being the only one that knows the private key, is the only one that can decrypt it. So you put the public key there. Here's an example of obfuscation transform. Let's say we have this simple program like if A, where A is some logical entity, then you do B, otherwise if else if C, that's true, you do D, else you do E. Okay. Well, they use frequently break the if else's down to inline executions. There's the inline conditional, which has got the question mark and the colons, which goes if A, then B, else, if C, then D, else E, which is the same thing as we see up here. They changed the if else's to the conditional operator. This, most humans don't read that well. When I taught the Java language, beginning Java class, I taught them how to do this because every now and again you'll see it, but it's more difficult to read than the other form. If the program has a loop, they often change it to recursion. I can tell you, having taught for 30-some years, students don't like recursion, and you could easily fool most of the students that I know if you use recursion instead of loops. Change the variable names and move on indenting. Here's an example. We have a simple little program, local variables, multiplication, doesn't really do anything interesting. If this is true, the box. Okay. Here is the obfuscated version. Okay. They changed all the variable names to V1, V2, so forth. And that makes it more difficult for humans because it's just a numerical. Of course, the compiler, works perfectly well for the compiler. It maybe even better. Takes out all the white space. All the if statements were converted to the inline ifs. Constants were propagated. This one had 7 and 8, so it used 8 and then just subtracted 1 from it if they wanted the 7. Here, this is interesting. V1 left arrow 2. That's logical shift. That's actually arithmetic shift to the left. And if you take a variable and you shift it binary 2 bits to the left, it's the same thing as multiplying it by 4. And the program had a multiplication by 4. So instead of multiplying it by 4, they shifted. It's actually faster, but it doesn't look the same. There are disadvantages to this. The biggest disadvantage, if you obfuscate the code and then there's a problem, you're trying to debug it, it's darn hard to figure out what it was doing. It takes, of course, another step to build this. You have to write the code. You would write it as you normally would. And then you'd run it through an obfuscation program. Then you compile it. And yes, you don't want to do this manually because that's very likely to create errors. Now, a lot of people want to obscure malware because the whole purpose is to make it difficult to understand. They don't want you to recognize that this program does more than advertise. Think about a Trojan horse. A Trojan horse does something that you want and something else. If you look at the source code and it's obfuscated, you might be able to figure out it does what you want. You might not easily see that part of the code that you don't want. So again, it's a means of making it difficult, but not impossible to figure out what's going on. Okay, any questions about that? Obfuscation and reverse engineering, brought to you by Lawrence Livermore National Lab. Okay. Then let's go on to the next step here, where, we seem to have lost. Stay tuned. All right, the review slides. Let's look at these. Okay, hopefully you can see the slides now. You don't want to look at me for sure. All right, I like this quote. It's not at all important to get it right the first time. It's vitally important to get it right the last time. How true that is. Okay. There we are. Final review. A reminder, course evaluations are out there on Blackboard. Please do them. I'll have you know that Comp 620 is way ahead of Comp 422 as far as doing the evaluations. I don't know who did the evaluations, but the university frequently gives me statistics on how many students have done the evaluation in your class. And a good number of students in the 620 class have done the evaluations. A miserably small number of students in 422 have done the evaluations. They are important. The university cares a lot about them, probably more than they should. So please go out there and do them in all classes, not just mine, but all of them. All right, what's going to be in the test? Everything. Everything we've talked about since the beginning of the semester could be on the exam. Having said that, let me be a little bit more specific. I wrote the exam already. I know what's out there. It's not everything. Here's the list. I just went out to the syllabus, got all the topics on the syllabus. There they are. Those are the things that we have. There's a lot. This is a cumulative exam. It covers all the material since the beginning of the semester, all these topics. But let's go over what's important. There are some things I thought were more important than others, and let's cover that. And I will at the end give you some hints about what you might find on the exam. All right, encryption. You should know about the different types of encryption. There's symmetric encryption like the AES or DES algorithms, and then there's asymmetric encryption like RSA, Diffie-Hellman, and some others. When do you use one? When do you use the other? What's the advantages of one or the other? Also, digital signing. How do you create a digital signature or a message authentication code? How do you create those and with what algorithm? And when do you use one? When do you use the other? Here's something I didn't talk about because it came out. I read an article in the IEEE Spectrum that came out a month or so ago. Since the beginning of this, since we talked about encryption in class, I read an article that talked about quantum threats to cryptography. Okay. The National Institute of Standards and Technology, NIST, is developing standards that will be secure if or when we have quantum computers. As I'll explain a little later, I'm not a believer in quantum computing. Doesn't exist now. You can, right? I may be wrong, but I don't think it'll ever exist. So, but there is always that concern that maybe somebody will figure it out. They have yet, after 40 some years of working on it, they haven't got it. And I don't think it's possible, but somebody might. It's made a lot of faculty members employed. But okay. But if they do it, you want to start working on quantum proof software now because RSA is out there. RSA is very popular. Almost everybody uses it, hybrid computing. And so if you're going to change over to a different algorithm, you better start switching now because if the headlines tomorrow are somebody's got quantum computing to work reliably every time and they can do these algorithms, then RSA relies on the difficulty of factoring large prime numbers. If you remember, you get two prime numbers, P and Q, you multiply them together, you get N, and so forth. There's more to the algorithm, which you should know. And it's difficult because it's very hard to factor N into both P and Q. There is a quantum algorithm that does that. So if you can do that quickly, then you can break RSA and it's no longer an effective encryption algorithm. They have other alternatives that are effective against quantum. They believe that quantum computers will not provide an improvement in solving these algorithms. They mostly have a key encapsulation mechanism that allows two parties to share. Now, think about encryption. Generally, like hybrid encryption, if you like TLS uses transport TSL, transport security, transport layer security, TLS. First, uses public key encryption, RSA, to send a AES key to the other side. That's typically how it works. So you don't have to encrypt much. It makes a random 256-bit key and then encrypts that with RSA, sends it to the other side decrypts it, and now you've got a shared AES key. And after that, everything you send is encrypted and decrypted with a symmetric key, AES. So very little is used for the actual RSA encryption. They use it to share keys. There's another way to share keys that's quantum proof. They have the key encapsulation mechanism that allows you. Here's basically how it works. Okay, Alice wants to send a message to Bob, and they want to share a key. So instead of encrypting with RSA, Alice runs the key generation algorithm on her computer. She then sends two outputs. Well, there's two outputs from the key generation. She sends one to Bob. She keeps one. Bob runs the encapsulation algorithm given this, and that generates two outputs. One of the outputs he sends over back to Alice, and then Alice takes that with the decapsulation information, runs it through the decaps, and that creates the shared key. Bob also has the identical shared key. So both of them have the key. It's exactly the same key. The information going back and forth does not provide you enough information to generate that key, and it's expected that a quantum computer cannot solve this in a reasonable amount of time, any faster than a traditional computer can. So again, it's replacing the RSA portion of hybrid encryption to share keys. Okay, that's quantum proof computing. All right, you may want to know about policy models. Remember in the beginning of the semester, we talked about the Laputa model and the Biba model. And if you remember, the Bell-Laputa model provides confidentiality. You can read down. That means you can read at the same level you are, or you can read at lower levels, but you can't read at higher levels. You can create a file at a higher level. The Biba model works in reverse. You can't, you can write up, but you can't, or excuse me, you can read up, you can't, and you can write down. You can always write at the same level. That's Biba. Biba is an integrity model. The dominating relationship. This is important. This is what the whole thing of those Bell-Laputa model is based on. You need to know that. Because at any time you're wondering, can I read or write this? Just think about the dominating. In order to read a document, you have to dominate it. In order to write a document, that document has to dominate the user. So the user dominates the document to read it. The document dominates the user to write it. So again, some examples here. This top secret in the categories grad and faculty dominate secret grad because top secret is a higher level than secret, and grad is a subset of grad faculty. Same thing for this one. Top secret does not dominate. Top secret with the category grad does not dominate confidential, even though the level is higher, but this has got a category that is not in the user's category, so it doesn't, so you can't dominate. Okay. That's important. You want to know that. Authentication. Talked about authentication. There's different ways to do it. There's the basic, what you know, that's like a password. What you have, that's like a security card or key. Where you are, you can base it on physical location, or you can base it on network location. What's the, no. Here in campus, you can access the banner system if you are on campus. You can't from off campus. What you are, that's biometrics. Biometrics measures all sorts of, there's fingerprints, there's iris, there's retinas, all sorts of things that determine, is this really you? And then what you can do, there are little tests to see if you can do something that other people have a hard time reproducing. Input validation. A lot of the security can be improved by input validation, making sure that you don't have it. Parameter tampering. Make sure that users don't change parameters, maybe even outside of the browser. SQL injection, cross-site scripting. All these involve taking user input and putting them in there. Never execute user input. Even if you think you sanitized it, there are tricky ways to get around sanitation. Modifying parameters. Remember this, where when a user clicks on something in their browser, it sends a message off, it sends the parameters. Parameters are sent off. You have your URL, question mark, then followed by parameters, and they are name equals value, separated by ampersands. And so here, this one has the price. Oh, they're sending the price back to the server. That's pretty silly. The server probably knows the price. You should not send it because this could be intercepted. Several ways you can do that. You can use an HTTP proxy like ByteSuite or Zap, the OWASP one. There's browser debugger. Sometimes you can use the debugger. Another easy way you can do it is copy the source code. Like you're looking at this web page in the browser, just right click, save it onto your file, and then in your copy on your disk, edit it to change the price. Sometimes if you do that, when it executes the send, in other words, if you're in a form and you do the submit, it's going to send it off someplace. On some web pages, they'll just give the name of the program. They won't give the full URL because by default, it goes back to where it came from. If you've copied it, you may have to add the full URL, but that's okay because you know where you got it. Just go click where you got it, copy, paste it into the copy of the program, and then it will work and at a lower price. Guessing games. Again, when you go out there, I had a file had this, you can look at this one. Well, that's actually not that's an old website, but HW3SOL. All that contains solutions to homework 3, right? You probably figured that out. Well, if you're doing homework 4, you might, just for fun, go out and see on the website if there was an HW4SOL PDF that has the solutions. That might be nice to know before you turn in your assignment. And this same sort of thing occurs in many industrial commercial situations where people have obvious names to web pages that you might not want them to know about. There's an easy way to fix that. You can just create random numbers, create a random string of characters. Just take a random number generator, use it to create random characters that are long, like 32 characters long. No one's ever going to guess this thing, not in their lifetimes, and use that, so they'll never figure it out. They can't guess what that is, so they won't be able to look ahead. Network security. We have several. Now, this is not the network security course. There is a separate course to that. I think Dr. Shu teaches that, but he's taught it in the past. We have ARP poisoning. That again, where ARP is the address resolution protocol used to find out. Oh, Cassandra teaches it now? Yes, okay. Dr. Shu used to teach it, but now Cassandra teaches it. Okay, that ARP is to find out the hardware address on a local area network for a given internet protocol address. DNS poisoning is where you change the address in a domain name server that converts from internet names to internet addresses. And then, of course, there's also firewalls. Firewalls filter the packets going through based on whatever criteria you want to give them. Malware. There's all sorts of malware out there. We talked about this. There's viruses, worms, you can see the list. Viruses are programs that modify other executables to propagate their worms are also propagating. They generally don't modify other programs. They just try to propagate themselves. Trojan horses are programs that are made to do something that you might want to do, but in the background, they do something you probably don't want done. Rabbits are programs that rabbits are programs that consume all the system resources. They showed the fork bomb, and many people did all sorts of rabbit programs in the last exam. Phishing is very important. And then rootkits. We had our Google exec talking about cloud security. Just real quick reminder how clouds work. There are 3 different cloud models: infrastructure as a service, platform as a service, software as a service. And of course, there's on-premise means that's a traditional way, you just do it all yourself. If you get a machine that's infrastructure as a service, then the cloud provider gives you a virtual machine and you boot your own operating system on it, run all your own software, it's all yours. If you have one that's platform as a service, then they provide the operating system, the middle and the runtime, and you just provide your applications and your data. For instance, on the class website, they provide the web server program. I put the PHP programs out there that are the other end of the web pages. At the other end of the final exam, I've been out writing PHP programs and HTML to write the final exam. So it's out there. And then there's software as a service where they have everything and you just provide your own data probably. I found an interesting analogy for that is pizza as a service. Okay, the on-premise version, whereas you make the whole thing yourself. You make the dough, you make the pizza sauce, the whole thing is yours. Set the table. If you have infrastructure as a service, that's when you go out and you purchase a frozen pizza from the store. The company gets the cheese, the toppings, the tomato sauce, and all the dough, and they sell you that. You have to cook it, serve it, and get things to drink. If you get pizza as a service, which is like having the pizza delivered, they do the whole thing. They cook it, they make it. All you have to do is put it on the table and provide something to drink. If you're dining out, that's like software as a service. They provide everything. They make the pizza, cook it, and provide it and give you drinks. So I like that analogy to different levels of cloud. All right. What should you know next Monday? Hint, hint, hint. I suggest you know when and how to apply different versions of encryption. I would not forget how to do SQL injection. Understand cross-site scripting and how to do that. I love Bell the Poodle model accesses because usually those are multiple choice questions and Blackboard will grade them for me. I like that. And also know how to modify form parameters. Okay, there's more to the exam than that. That will be on the exam. Okay, what do you want to get ready? Well, this exam is similar to the last one. Look at the previous assignments, look at the past exams. I don't know if any question is exactly the same as a past exam or past, no, I'm pretty sure it's not. I think I intentionally avoided reusing questions, but they're similar. So yes, if you can do the stuff, so if you look at past exams, if you didn't get the exam 100% correct, then look at those things you got wrong and understand how to do them. Okay, format of the exam. Just like all the previous exams, it's going to be on Blackboard. It's going to be online. It will start at 6 a.m. Yeah, Blackboard will work. To tell you the truth, the university was going to do some maintenance this weekend. I emailed Mr. Jackson, the head of IT, and said, look, people are going to be putting in final grades on Monday, right after you do the maintenance. As they proved last time, maintenance may not work the way even what you think is a simple upgrade may have errors and things may not work. And I suggested, and they took the suggestion of moving the maintenance back a week. Everybody will be gone. All the students will be gone. The faculty will be gone. The grades will all be processed. If it screws up, nobody will ever notice. So, yes. But I mentioned that to him. Why did I think about that? I've been in his shoes before. I was manager of systems programming at another university, and we only did our maintenance. We tried to schedule our maintenance like right as the beginning of fall break. So if it broke, we could fix it before anybody was concerned. Same thing with we kind of stayed there during holidays, so other people wouldn't notice. Okay, 75 words or less. That means if you go out to AI and you copy and paste the question and you get an AI answer, and it's longer than 75 words, you can copy and paste that answer into another AI system and tell it to summarize it to 75 words or less, right? Let me tell you, I've run all these questions through an AI system. If the AI system gave me a good answer, I didn't put it on the exam. Little logic, if then else. If AI gives a good answer, it's not on the exam, you can reverse that and say, if it's on the exam, AI doesn't give you a good answer. Take that as a hint. Okay. if at any time during the exam there's a problem, if you don't understand the question, if Blackboard's not behaving or something, give me a call, or actually, prefer you email me, call me, text me, and I'll try to respond as quick as I can. Oh, some people are exempt from the exam. If you got an email from me and the email said you are exempt from the exam, then you are exempt. If the email I sent to you about your grades did not say you're exempt, it would say you must take the exam, then you must take the exam. If you don't take the exam, boy, it's going to have a really significant negative impact on your grade. So take the exam if you are exempt. Some people are concerned that, oh, what if I do poorly? I'll make you this promise right now. If you're exempt and you take the exam and you screw up, I'll just throw it out. So you can't lose. You can only do better. So if you think, well, maybe I could try, maybe if I have to get a 91, maybe I could get a 91 and my grade will go up. Give it a shot. If you have to, besides, if you're taking the exam and you realize, oh, this is not my day, I just can't remember this stuff, then just press the cancel button at the end. Do not save your work, and send me an email saying I'm not doing it. Well, it doesn't really matter because I will not give you a worse grade if you try with an exempt student. Now, if you're not exempt and you screw up, well, that's too bad. Your grade may go down. All right. That's enough. Any questions about the exam? Don't run away yet. Wait, there's more. Oh, okay. It's an old poem, but I like it. Okay. This is my last lecture. I don't know if I'm teaching next year or next semester. I'm not teaching next semester. I don't know if I'm teaching next year or the year after that. This may be it. I'm old. I'm not old like your parents. I'm old like your grandparents. I mean, I'm 71. It might be just time to hang up my chalk and stop doing this. It's been enjoyable doing it, but it does take time. Okay, so some people, what is this old white guy doing at a back university? I'm doing very well, thank you. I've been here for a long time and never, ever, and since 1992, you can do the arithmetic, has anybody ever mentioned that ever been a problem? And I credit that to the quality of the students we have here at A&T. This is the biggest and best HBCU. All right, some things to think about. This has little to do with, well, sometimes it has to do with computing, but it has a lot to do with your life. Will this be on the exam? It will not be on Monday, but it might be on the exam for the rest of your life. So think about some of these things. Yes, balance your life. There's, don't spend all your time working. It's easy to do. Sometimes you figure, you're doing this for your family, right? I mean, you have to make money to support them. You want to do the very best you can at work. And so you're out there. So you're going to do the best you can. So you get the raises and you make money to support your family. Yeah, but you can do that and still pay attention to your family. Trust me. And it's easy. It's easy to not spend as much time with your family as you think you should, as you probably should. Very rarely does one spend more time with their family and less time with the work. And I'll tell you, nobody lies in their deathbed that I should have spent more time in the office. Another thing is if you're going to succeed, if you're going to learn, you're going to have to work at it. AI systems are not going to do it all for you. You're going to have to spend some time. Oh, several years ago, there was a study going on with several universities. I can't remember who was funding it, but I was helping out here at A&T. We gave questionnaires to students, and then they gave questionnaires to students at several other universities, and they compiled the results, and they learned several things. One of the disturbing things they learned is the students at A&T spent significantly less time studying than at other universities. At other universities, some of the students spent a whole lot of time studying. They not only went to class, but they'd study the usual twice as many hours outside of class as inside of class. Not very many A&T students do that. So when you get to the end, well, maybe the A&T students are just so much brighter and better than the other students, which is a possibility. Or the other students worked harder, they learned it better, and they're going to eat your lunch. So you might want to think about that. I just mentioned this was the results of a careful study that was made. I'll also tell you that if you want to succeed, going to class is not all it takes. You need to get involved. You need to work with the faculty, work on some projects. There's all the faculty have projects going on. Some of them even have money to give you. So work on some of these projects, particularly if you're a graduate student. Graduate students don't do the class option. Do a thesis or a project. Projects are easy. You can do a project. Project, in fact, is better than a class. All you're doing is replacing one of the classes with a topic that you care about, because you get to pick the topic of the project or the thesis. Of course, you have to work with a faculty member, and you've got to convince the faculty member that they care about the project also, but it's a topic of your choice. Otherwise, you work in a class that we get to decide what it is. So projects are just more fun than a class. Try as I might to make this class entertaining, projects are more interesting. So, and you get a lot more experience and deeper understanding. Also, internships are really good. Do I have that? I don't know if I have that on the list. Internships. There are companies that don't want to hire anybody unless they've had an internship. Not necessarily with them, which is, of course, very good, but maybe with somebody. Companies like you to intern, and then if they really like how you did as an intern, often they'll make you a job offer because they've seen you. They know what you can do. So recommend internships. Software engineering. I don't teach software engineering. I'm not a software engineer, but it's very important. People have this agile software engineering tech, but you have to know where you're going. You have to know what you want the software to do. Because if you don't know what the software is going to do, well, then almost any software will work if you don't know what it's supposed to be. You have to have an idea what it's supposed to work towards that. And I can tell you, long ago, when I was a grad student, I had an outside job working for a small startup. They had a software product that they were selling and modifying, and they were making an upgrade. And they had a very vague concept of what the new version was going to be. The old version wasn't working well. They knew they needed a new version that worked in a different way. They knew the different way they wanted, but they were not very specific on how they were going to get there. And they never made the new version. They spent all their money hiring programmers like me to modify their system so that they could get to the new, but they never did it because nobody was really sure what it was. Nobody was, they kept different programmers writing things, but they didn't have a common goal. So they lost, eventually they went belly up. I mean, when the president comes around, hands you the paycheck and says, cash it quick, that they may be in trouble. And they were. They eventually went bankrupt. Somebody should turn their phone off. Sorry. But software engineering is important. Understand what it is. You can't write program if you don't know what it is. Okay. Computers have changed. I have been writing programs for over 50 years, and computing has changed. I tell you this because computing is going to change in your lifetime. It'll be a big difference by the time you're old and gray like me from what you started with now. It will change a lot. Again, computers used to be huge and expensive. They used to be $1 million machines, and they wouldn't fit. They barely fit in this room. In fact, this is Graham 208. If you go to Graham 210 next door, this used to be the university's computer room. You wonder, why did they brick up the walls, the windows? Well, they didn't want anybody sneaking in through the windows and carrying this, 10,000-pound computer out the windows. But they were concerned for security. They bricked up all the windows. So this is it. It was huge, and the computers were big. You can see in this silly picture, people here, computers took up huge room, and they took a lot of electricity and a lot of air conditioning. They had operators. I mean, you had people who wrote the programs, but you also had operators. They were like the hourly people, and they kept it running. They did what the computer asked. They mounted tapes on the tape drives. You can see tape drives in the back, and they did other things. They started programs and took the paper off the printer. You had big and put it where it was supposed to go. And the operators were usually on the job training. You hired a new operator and they worked with another operator for a day, and then you're on your own. But a good operator really helped. Good operator learned how the things were watched. Back in those days, the computers had these winking, blinking lights. And some of the really good operators could look at the winking, blinking lights and say, I don't think the system is working correctly today. There's something running wrong. It's not, the lights aren't blinking like they should when they run like the payroll program. They had looked at it enough. They knew how they should blink, and this is not how they should blink. So it's time to call the payroll office and say, I don't think your program is working correctly. Computer rooms were locked. Well, in order to get into computer room where I worked for the university, because you had to get in the building, you had to put your card in the slot and type in your code. Again, you had to do it again to get into the computer room. A lot of people could get in the building. Only a few people could get into the computer room. And then you had to walk right past the operator, who was sort of a casual security guard. You could walk, because they would look at it and say, if somebody walked in, like, who are you? They knew who was supposed to walk in. In fact, we did have a company come in and do a security check, and the door to the computer room had a slide open. You could put, you wanted to give the person like something. You wanted to give them a deck of cards or something that you needed to give to the computer operator. You could put it on open the door, put it on the little, it was only like a foot by 6 inches. And when we had a computer security test, the people at the testing agency came in, somebody tried to put their arm in the door and see if it would fit. And the operator goes, whoa, what are you doing? Put your arm in the door, get that out. I will tell you, a 6'7" fellow who worked for us, his arms were so long that he could reach in and open the door from the inside but nobody else could. Okay. But important thing about that, yes, it's because people had a heart, they couldn't get into and touch the computer. There were a few terminals outside in offices, but that was it. If something broke, you're going to have to fix it. So we tried not to break it. And only a few select people were allowed to use the computer. Now, everybody in the world can use your computer. It's the World Wide Web, and they can all access your computer system from the web. And so who knows what's going on? You have to be very careful. If back in the old days, we were more concerned about computer security, we wouldn't be so concerned about it today. We would have built things with a lot more concern about security. Nobody cared about computer security back then because it just wasn't an issue. And so a lot of software was generated, and it became the norm that we would generate software without any concern about security. Now, hopefully you've learned in this semester that computer security is very important, and we have to build it in as we're creating the software. Another thing the old professor will mention is efficiency. That IBM 360 in the picture, an iPhone, the current iPhone's 25,000 times faster than that machine. I mean, that machine cost millions of dollars. It wouldn't fit in this huge room. And the iPhone is 25,000 times faster. So I hate to say this to the algorithms people, take the Comp 285 algorithms class, but way back then, efficiency was important because things were slow. You'd run your program and it would take a measurable amount of time. You could sit there and watch it until it got the answers. It was slow. And so efficiency was, if you wrote a more efficient algorithm, you could see that it was more efficient. It was faster. Now, most programs finish in the blink of an eye. There's little advantage in running and finishing in half a blink of an eye. Of course, as the program gets bigger, It may be that you need to run the program on lots and lots of data, in which case efficiency does become important. I've got a program I ran that took 35 hours to run on a pretty fast computer. Yes, with a little bit of data, it ran quickly. With a lot of data, and it wasn't a lot of data. It was a very inefficient algorithm. It was the best I could come up with. It took a long time to run. But most of the time, things run very quickly. So efficiency is not the top thing. Correctness is so much more important. It's so much more important that your program is correct, because if it gets the wrong answer, it doesn't matter if it gets the wrong answer very, very quickly. No good. You have to get the right answer. The right answer fast is nice, but the right answer is much more important than getting the wrong answer quickly. Okay. Here's old Dr. Williams's guesses about what computing is going to look like in the future. I'm not sure about disks. Nowadays we have cloud computing. People are keeping their stuff in the cloud. I'm not sure how that's going to work. There's still lots of things you probably want to keep locally on the hard drive. And it may become, so why bother with thinking like this? The hard drives are no longer the slow rotating memory. They are chips. You have flash memory. You've got solid state disks. The solid state disk is only slightly slower than your RAM. And so at some point, they might just come up with memory. It's the same speed as your RAM. And then why bother differentiating between this is your disk and this is your RAM, like we do now? And just say it's all RAM. And that has some implications. How do you access the data? Well, you just access it by virtual memory. Imagine virtual memory, where you have certain addresses represent your program, and then you can map in this, what you think of as a file, as part of your program. You just access it as if it's a memory. Widespread connectivity. Well, you've got just about beat that one to death. Everything's connected to everything now. But that also, as I mentioned last time, has its dangers. If something breaks, everything breaks. AI systems we use to filter out what's going on. Google Glasses. Remember Google Glasses? They were out and they kind of came up. They're glasses you wore that had a computer and could look at things. They did some interesting things. They could do face recognition. You could look at somebody in your Google Glasses and suddenly it pops up and says, oh, that's Joe Smith. Which is kind of nice, particularly if you're old and gray and you can't remember people's names for anything. Also, people talk about self-driving cars. That's interesting, but that's not where the money is. The money's in self-driving semi-trucks. The big trucks, they pay people a lot of money to drive those trucks. Those guys make a lot of money, and they can only work like 8 hours a day. If you have a self-driving truck, it can run 24 hours a day, and once you buy that truck, you don't have to pay the guy to run it. They got to resolve certain things like how do you fill it up with new gas or new diesel fuel, but that's a solvable problem. So you can expect self-driving trucks. Also, self-driving trucks spend most of their life on the freeway, where driving is easier than in town, safer. Though having said that, you remember that several semis had accidents Tuesday morning, but that's, yes. Okay, quantum computing. I think I said earlier, I'm not a big promoter of quantum computing. It may occur. I don't think it will. It's been out there for 40 years. They've been saying, oh, it's just around the corner. It's always been just around the corner. They just have to figure out how to resolve that problem of the error rates, and then they'll have it. And they're getting better, and they're getting better and better, but they're not there. They may get there. I may be wrong. I don't think so. So I wouldn't put my money on quantum computing. As I mentioned last time, be sure to back up your files. Systems break. Watch out for that. Be ready. Save your money. You're going to go out and get a job. You're making more money than you ever made, working at McDonald's in the summer or something like that. Particularly if you happen to be unmarried at the time and no children, then you might have more money than you need. Save it. You don't need to spend all your money. You don't need, some people go out there and they buy expensive houses and expensive cars and can barely afford to eat because they're paying large mortgages and large car payments. Be a little more frugal, save your money. It works well in the long term. The money you save when you're younger becomes a lot of money when you're old and gray. Here's an example. Okay, the last 40 years, stock market has averaged 11.69% return. Actually, I think it's a little larger now. That was a couple of years ago, but it's a pretty good return on average. There'll be bad years, there'll be good years. On the average, it's done pretty well. Just imagine you take $100 a month and you save it in a place that gets 11.69%. You'll have spent $48,000 total. That's $1,200 a year, it's $48,000. If you do that, and you have 11%, 11.69%, you'll end up with $844,700. That's a lot of money. That's a lot more money than this. That's almost $800,000 more. That's a lot. And when you're old and gray, you want that $800,000. Social Security may or may not be there when you're old and gray. I thank all of you for supporting my Social Security. I appreciate that. Hopefully there'll be somebody there to support it when you're old and gray. They're going to have to do something because it will not continue to work the way it's working now. Okay. Be active in your community. Do things. I've lately tried to work for the Red Cross. I actually went out to the Red Cross and somebody had a house fire. Red Cross went out there with our Red Cross blankets and we could give them money. Red Cross is a temporary, immediate help. We don't fix the problem, but for people who are standing there with no more than the clothes they're wearing, looking at the burning embers of their house, Red Cross will come by and help them out, give them some money, help them get going, get new pair of glasses and some medicine if that's what they need. So do things, help out. Yes, help people. Makes your community better. Vote. Go out there and vote. We can even run for office. I suggest you stay physically active. Right now, you're in pretty good health, I hope. You're young. Let me tell you the sad truth. This is about as good as it gets. Those of you who are about 22, 24 years old, it's a bobsled to hell from here. It's not going to get any better. So stay healthy. If you do physical activities, find something that you enjoy doing. Do something. Hey, pickleball. Old folks play pickleball, although the national champions for pickleball, these young people, I don't know who let them play. But yeah, I like to run. So I go out and I've been running for decades. So find something you enjoy. Besides keeping you healthy, it also provides an outlet for you to do things. You can have a fun thing you can do every week. I have a bunch of friends from the running groups I belong to. And again, I may be slow, but I'm faster than that guy on the couch. And the last thing I want to leave you with is be nice. Be nice to people. It'll be good. It's good for you. It's good for the universe. Be nice. You need to respect the inherent worth and dignity of every person. So that's my closing words for this. So go out there. Good luck on the exam in this course. Good luck on all your finals and good luck in life. So that's it. Thank you very much. End of the semester. All right. Anybody online have anything to say? Bye. Okay. Oh,
I really enjoyed your class.
oh, good.
That's exactly.
May I have my cards back, please?
Thank you, Professor.
Oh, yeah. Yeah, I'll handle them. Oh, here, put it on the table so all right. Okay, let's see.
No, I'm afraid not. Look in the next topic, remember, don't quit. Because usually the tour browsers, you go to grips, everything, they can't tell where you're going. That's the thing about tours. Before, the way you tell where you are, you can't tell who's going to. Counts, yeah. And you can't even tell where it's going because before, obviously things on multiple relays to get them, so they can't tell. And we need 5 points, but that's it. Didn't mention that. But that everybody is in the place, you just can't tell. It looks like the privacy question. Huh? Like you really- what browser? Okay, so, what browser is footnotes? At MIT, you use the Tor browser to send a bomb threat,
Oh.
so that you can get out of the test.
Yeah,